Okay, so I was looking at this example, trying to find a recursive definition for this set of all multiples of 3 or 5 among positive integers. And I tried doing things like multiplying things together in the set, but that doesn't give me everything because I couldn't get 6. I tried adding things, taking things that are in the set and like adding 3 or 5, but then I can do 3 plus 5, which is 8, which is not in the set, right? So I got a bit stuck, but I came up with a good way, a decent way to say how to do this. So let's start with the same base case. 3 and 5 are both in S, right? And then for the recursion rule, I want to be a little more precise. I do want to stick to the adding idea, actually. I want to say, hey, if I've got a multiple of 3, if I add 3 to it, I have another multiple of 3, right? And by continually adding 3 to multiples of 3, you're going to get all the multiples of 3. Likewise with multiples of 5. So I want to do adding either 3 or 5. But what I need to do is I need to incorporate a check. I need to check to see if the element that I have in the set already is already a multiple of 3 or already a multiple of 5. Because you don't want to take something that isn't a multiple of 3 and add 3 to it. You only want to add 3 if it is a multiple of 3. So since our recursion rule can be in the form if-then, I can put other conditions into the hypothesis of the if statement, right? I can put other parts in the if. So I'm going to say if A is a multiple of S and A is a multiple of 3. Sorry, I misspoke earlier. If A is an element of S and A is a multiple of 3. To check to see if A is a multiple of 3, I'm going to use that operation from number theory back in chapter 4, where you do division and take the remainder. So I'm going to divide by 3, take the remainder, and see if it's 0. That's the mod operation. So I'm going to do A mod, I don't know why, I'm going to get rid of that underline there. A mod 3 equals 0. So if A is an element of S and A mod 3 equals 0, meaning it's a multiple of 3, then A plus 3 is also going to be an element of S. And I can do the same thing with 5. So I can incorporate multiple if-then statements into my recursion rule that are all going to be applied. If A is an element of S and A mod 5 equals 0, then I can say A plus 5 will be an element of S. So now what my recursion rule is essentially doing is taking elements that are already known to be in the set, checking to see if they're multiples of 3 or 5. If it's a multiple of 3, add 3 to it to get a new number. If it's a multiple of 5, add 5 to it to get a new number. So let's take this recursion, that recursive definition that I've written here, both parts, and let's check to see if it works. So in the 0th case, I just have 3 and 5 from the base case. After applying the recursion rule once, I do both of the if-then statements. So take 3. 3 is a multiple of 3. So 3 mod 3 is 0. So I can apply this part. So I'll be able to do 3 plus 3 to get 6 in that step from this rule. If I try to use 3 in the second rule, 3 is an element of S, but 3 mod 5 is not equal to 0. It's equal to 3. So that would not apply. However, with 5 is in S and 5 mod 5 is equal to 0. So I'll be able to do 5 plus 5. So I'll get 10 from this one. And that'll be all I get. So I get the new elements 6 and 10. Then in the second application of the rule, I'll have some new things to work with. I'll have 6 and 10 to work with. 6 is a multiple of 3, so I'll get to add 3 to it. So in the next step, I'm going to get 6 plus 3 is 9. 6 is not a multiple of 5. 10 is just a multiple of 5, so I'll get to add 5, and I'll get 15. And I want to do one more step because I want to show you what happens with 15 in particular. So in the next step, I'll get to take my new numbers. It's like I'm always taking the new numbers and working with them, right? Because the old numbers, if I work with the old numbers, it's just going to give me elements I already have. So I'm taking the new numbers. So I've got 9 and 15 now that are new. Take 9, I'll be able to say that's a multiple of 3, so I can add 3 more, and I'll get 12 from that. But 9 is not a multiple of 5. Take 15, well, that is a multiple of 3, so I can add 3 to that and get 18. But 15 is also a multiple of 5, so it'll count here or here, and I'll be able to add 5 to 15 and get 20. So most of the time, so for the first 2 applications of the recursion rule, we only get 2 new elements in the set, but in the third application of the recursion rule, we get we get 3. I don't know what just happened. We get 3 new elements, and that's because 15 was valid for both of the 2 rules, right? 15 is both a multiple of 3 and 5, so we get to add 3 to it, and we get to add 5 to it. And this recursion rule should now generate the entire set S that we want, and exactly the set S that we want. So there we go. So that was the end of example 2. This is with sets. I think I'm going to do one more example for 5.3. And then we'll be done.